The Tagi reservoir itself, it was also well imaged. We interpreted both the base and the top of the Tagi reservoir, and some shallow markers, the D2 and the continental intercalaire marker, have been interpreted to do some backstripping and flattening of the some key horizons. This is a kind of zoom within the Tagi section. We overlay some logs, the sonic log and the gamma ray logs, and highlighting the different units of the Tagi reservoir and showing the good data quality within the Tagi. Right, and we can see good correlation and fit between the different, seismic events. At the deeper section, we have some events. They are obvious at the seismic and they are absent in the synthetic, and most likely they are multiple, events generated by this evaporitic and carbonate section with high velocity of Triassic and Jurassic age. Moving now to the depth conversion, we used some simple average velocity function to convert our time maps, and we can see some gentle variation of the velocity, and it's following, the deepening of the basin toward the southwest. The graph of depth versus time is showing quite simple and sublinear variation of the velocity trends. Now the last part is the structural interpretation over the Borma fault splay. So this is the Ordovician depth map showing the geometry and the configuration of this fault splay. We can see in the detail that our fault is composed by two branches, the east-west branch and the northeast-southeast branch. At the Ordovician level, we can see the normal fault component at this level. We can see the downthrown side with some rollover structure formed, in the downthrown side of the fault, whereas the northeast-southeast branch is showing more linear and elongated anticline along this direction. And we have the small throw of the fault, along this direction. At the Tagi level, we have, change of the geometry and the configuration of the fault. We start having some kind of branching geometry and sinuous geometry associated with some initial, structure, with associated structure at the east-west branch, and it's interpreted as kind of initial fault system of dextral relay, and with some associated structure, they are making kind of a small anticline, which consists kind of a transfer zone or relay ramp formed by this shear movement along this east-west branch. At the northeast-southeast branch, we have mainly some reverse component of the fault, and this different, behavior and kinematic of the fault and change of the kinematic is mainly related to the direction of the fault versus the main stress fields. So we have some dextral and shear component at the east-west branch and more reverse component at the northeast-southeast branch, and we'll see in detail across some key seismic lines this conclusion. This is a 3D view at this Borma fault splay and showing the different associated geometry. We have this kind of initial faults associated along the east-west branch and the inversion along the northeast-southeast branch. Now we generated some random line along the two branches of the faults. At the north, this is northwest-southeast seismic line along this east-west branch. We can see at the basement, at the Ordovician level, we still have some normal faulting and normal throw of the fault at these deeper levels, whereas at the shallowest level we have some inversion, and this is a nice example showing both inversion and normal throw at the same fault plane. And when we move a little bit toward the east and close to the northeast-southeast branch, we can see that نبدأ البافل. So close to the northeast-southeast branch, we can see we still have some normal faulting at the basement, but the division is a little bit, I mean, the normal throw is a little bit, I mean, less expressed, and we have more robust and more compression at the taggy level and at the shallowest intervals. Microphone. Okay. Now moving to the northeast-southeast branch, we can see clearly that the Ordovician itself is inverted, and we have more compression and more reverse, I mean, component of the fault along this northeast-southeast branch. The basement is showing, I mean, small normal throw at this location. We did some flattening at some key horizon just to restore, I mean, the evolution of the fault during the time. This is the nowadays, I mean, present configuration showing the expression of the fault. And we did some flattening at the Ordovician. At the Ordovician time, you can see, I mean, the normal faulting at the basement and at the basement. And the flattening at some shallow level, the D2, we can see some, we can see some rollover at the taggy and below. And of course, we still we start having some inversion at this level after orogeny. So general uplift of the Rdems basin, which is associated with some erosion and penaplanation of the Paleozoic section. And you can see before, I mean, the deepening, it was toward the southwest. Now we have a deepening toward the west. So we have an inversion, and we have, I mean, at the Burma fault splay, and this is caused mainly by this Ersenian orogeny. The post-alpine orogeny has accentuated and the pre-existing structure, and we can see clearly, I mean, this shortening and this robust structure, I mean, at the taggy and the shallowest marker. This is kind of some surface expression of the fault with some remote data just to highlight, I mean, the expression of this fault. This is satellite image showing that around this fault we have some expression of some anticline, such as the Burma anticline and Senghar field anticline. And this is shaded topography relief showing also the expression, some surface expression of the Burma anticline and Senghar elongated, I mean, along this branch of the fault. The gravity data is showing mainly this northeast-southeast, I mean, low gradient of gravity, which coincide more or less with the extension of the fault. We generated some sweet spot attributes. This is an example of variance attribute at the Ordovician level, and it's well highlighting, I mean, the expression of the fault with two branches, the east-west branch and the northeast-southeast branch. Another attributes were generated, the edge attribute and the influential data attributes, and they are well highlighting, I mean, the geometry and the expression of these faults within the 3D seismic survey, both, I mean, 2011 and 2008 seismic surveys. Just, I mean, here kind of fault analogs of Burma around the Rdems basin and within the Tunisian site. Of course, this study will be the subject of full presentation of structural review of the southern Tunisia, and it will be presented by my colleague Ahmed. Just here kind of correlation between this Burma fault and some existing faults within the area. We have this master fault, the Benefsej fault, with again this kind of branching and sinuous geometry such as for Burma fault. And along with we have several discovery, the Benefsej Sud and Benefsej discovery along this fault. And along, I mean, the change of the direction and the accommodation area, we have a kind of transfer zone. Along with we have some formation of some traps and structure. They are, I mean, good traps for mainly gas bearing. Here the expression of the Benefsej fault We can see the rollover at the ACAX level, and we can see the normal throw of the fault at the basement level and the Cambrian level. This is another attribute, the edge detection, highlighting again, this kind of lineament and fault with northeast-southeast direction. They are starting from Al-Burma up to Benefsij. They are linked by some secondary fault system with northeast-southeast direction. And the accommodation of these two systems is creating several traps and several structure, and they are kind of concentration of deformation between these two lineaments. And in between we have formation of different traps and different discovery related to these two directions. This is the conclusion, the interpretation of the new 3D seismic survey, constrained by some surface and subsurface data, allowed us a better understanding of this fault geometry and the traps and the topology of the structure related to these faults. The Burma fault is divided mainly into segments and branch with northeast and east-west direction. During the Hercynian and Alpine orogeny, this vertical extensional fault has been reactivated as transpressional structure with strike strip or reverse component, pending of the respective direction of the fault, east-west or northeast-southeast orientation. The hydrocarbon accumulation occur mainly in relatively subtle four-way deep closures. They are showing some gentle asymmetry, and they are mainly trending parallel to the main deeper faults. Just, I will to acknowledge our partner ETAP and El Thani for the permission to publish this work, and thank you.
Most of you see stop faults around the Hercynian component inside. Sometimes it's stressed that the other faults are processing are other flowers, our flower fault. And now we have to figure that this is switch on or reverse. Are there any errors?
Fault. The Burma fault, for example, at the beginning it's normal fault, and clearly we can see the normal component of the fault in the downthrown side at both Ordovician and basement side. But during the later orogeny, the Hercynian and the Alpine orogeny, this fault has been reactivated as wrenching or dextral fault or reverse fault, pending of the direction of the splay of the fault toward the major stress field. Along the east-west direction, we have dextral, motion and dextral wrenching, component, and along the northeast-southeast branch, we have an inversion. The inversion took place mainly at the shallower section, at the Taggy and the overlaying formations.
The second question is concerning the basement.
The basement, yes.
Is it just an horizon that you follow or another?
No, we used some key wells, some well in the area, we have this data, and we use the 2D data to tie this well with this 3D seismic survey, and we are confident about, the interpretation of the basement.
Thank you.
Reconstruction of the percent roof inside the surface concentration. As is message in the title,
Hello. Okay, thank you. So sorry for the little mess. So, so this morning we saw several seismic imaging issues, and one was about the static issue, and one was about the multiple issue. And in fact, in this presentation, I want to show you how multiples can help, in fact, solve the static issue. And so it's combining the two issues. And it's a kind of new methodology that has been applied on a case study from Tunisia. So the title, A Reconstruction of the Bay of Sand Dunes using Surface Consistent Deconvolution Operators, a case study from Tunisia. So I want to thank my colleagues, Anna Rivet, Damien Forest, Sylvie Bayon, Salem Trabelsi, Mohamed Chebil, Katia and David from CEG, and Mr. Abdelatif Touel from ETAP, and as well as Mr. Glenn Morley, who as a consultant helped us to put in place this flow. So, you know in Tunisia especially that a significant portion of oil and gas reserves lie in the seas of sands. And this can cause a problem to seismic imaging. You may be well aware of this issue. So seismic imaging in these areas can be challenging. Here I just put a cross-section from South Tunisia. And at the top, you can see that there is a very schematic near-surface geological cross-section. I have two layers. Layers of sand, a soft material with a rough topography, and a layer of hard rock. And you can easily see that just below the sand dune, of course, the seismic imaging is affected strongly, and you cannot see anything. Whereas below the consolidated rock, you have a good imaging. So this is well known, and this is due to the rough topography and the slow sand velocities. So we have a method to solve this issue, a very basic one. It's to strip off the dune layer. So ideally, if we had a lot of money, we would just use bulldozers to strip off the layer. But in seismic imaging, we have another method, which consists in correcting for the travel time distortions in this sand layer. And for that, we compute what we call a dune static term. This dune static term is expressed as the following. It's very simple. It's vertical. It's just the thickness of the dune, so the difference between the top of the dune. Oh, sorry, I don't see it. You see the first term, the surface of the dune minus the base divided by the velocity of the dune. The problem in this equation that we have two unknowns, the base and the velocity of the dune. And we don't know. As you can see in this little animation, we don't know where is the base of the dune. And it's critical for us to know where it is because it has an impact on the long wavelength static solution, so on the long wavelength structure of the images that we're going to interpret. So how to do it? How to build a reliable dune model on our seismic surveys? We saw an example this morning. We used to do it, and we still doing it by using sparse Hubble information, which can be several kilometers apart. But it can be very challenging as you don't know what's happening between these Hubbles, and sometimes you don't have a lot of confidence, you need a lot of addition of this Hubble, so it's not very easy. What I would propose in this paper is really a seismic data-driven approach, which is a bit original. And I will explain you the principle first before seeing on this case study, on South Tunisia case study. So it's a very schematic view where I have printed a subsurface image with a dune layer at the top and some geological layers at the bottom. Normally, in a seismic, we use primary reflections to try to image, for example, the base of the sand dunes. And these primary reflections, so they consist in, so you see your source and receivers, and you have one reflection, for example, at the base of the dune, and then it's bounced back to the receiver. And you can have you have these reflections occurring between the base of the dune and the surface. The issue that we have is that usually we have a very low fold and irregular near offset distribution. So it doesn't help us to extract these primary reflections at all. The second issue is that, as you can see, you have acquisition gaps. As you can see on the right, you have a missing receiver because you don't lay out receiver at the top of the dune. And the third problem is that our arrivals coincide in time with other very strong arrivals, like ground roll, like you can see in this first on the left, and refracted arrivals on the right. So it's very difficult for us to capture this primary reflection at the base of the sand dunes. What about using surface multiples? So this is an idea that we can have. So surface multiples, in this case, we're going to interested in one kind of multiples. The multiples that travel down to the base of the sand dunes, then they are reflected back at the surface, and then they go down to deeper layers, and then again they bounce back to the surface, coming down on the base of the sand dunes, and going to the receivers. And you have that. This is happening at every record. The problem is that they are very weak. You don't see them in the record. So this is our issue. We know that they exist, but we don't see them. But they have other advantages. They are very redundant. It means that for every reflection in the subsurface, you have these surface multiples occurring. And also, as you can see in this scheme, they are pseudo 1D. We can consider them, since we have very deep reflections, we can consider them a pseudo 1D. So all these characteristics, in fact, let us think that, in fact, these surface multiples are embedded in the source and the receiver signatures. So our issue now, and we're going to see how they are embedded, but our issue is to extract the source and receiver signatures. And how can we do it? How can we extract the near surface reflectivity from surface consistent deconvolution operators? This is the method. I will explain that in a paper that I published in 2015 in EAGE. So I will just recall briefly the methodology, because it works not only in dune environment, but in any kind of seismic land surveys. First, we compute autocorrelations on the LED reflected energy, like for example, it's a shot. So you just estimate which we call an estimation window. But so we're going to compute autocorrelation of this window to image the shallower part of the data. So it's about imaging the shallow from the deeper part of the record. Then from these autocorrelations, we're going to perform a surface consistent decomposition of these autocorrelations. So this is a global turn on the left. So it's decomposing a global turn. The source receiver is one trace, plus a shot and a receiver turn. Then, through a very classical deconvolution algorithm, which is a Wiener-Levison system, I will not go into too much mathematical details, we're going to produce some deconvolution operators, decomposed in one global operator, one shot operator, and one receiver operator. And the link between the deconvolution operator and the signature is that the deconvolution operator times the signature gives a Dirac. This is the link between the signature. So this is how. So we're going to look at these deconvolution operators and see how we can, from them, build a dune model. So for this, now I will go straight to the case study from Tunisia. First, Tunisia will recognize maybe most of you will recognize the field. So we have a topographical map with the dunes and the top of the outcrop of the hard material here. So you will see on the west dunes and on the south hard outcrop. And this is just a brief introduction to the acquisition survey that the dataset we are processing. It's a classical orthogonal surveys with 300 meters between source lines and 250 meters between receiver lines. So I want just to stress that the images that we're going to see are along the receiver lines, or along the shot lines. So we are limited on this sense by the sampling of the source and receivers. So this is what we get when we look at a receiver deconvolution operator from this survey. So it's in time. The zero is the true zero. It's from the surface, in fact. And what is interesting is that we see that on this deconvolution operator, so in these signatures, if you want, which is a bit the reverse, we see a strong event, a strong reflectivity, especially under the dune area on the west, and then on the left of the survey. What is interesting to note is when I plot the topography above this section, there is a kind of mirror image of the topography. And in fact, this reflector corresponds to the base of the dune that is mirroring the topography. And we have the same thing if we look at a shot operator. again, you see a very strong reflector distorted, which is a mirror image of the topography. And this reflector corresponds to the base of the dune. So we have a nice reflection of the base of the dune, directly from the seismic data, which is impossible to see on the primary reflections. Now, how to go to the depth? Because here, okay, we are happy, we are in time, it's a bit distorted, so how do you build a depth model of your base of dune? We're going to stretch to depth with a constant dune velocity. We're going to make an assumption in that case. I will explain you how. So we have the deconvolution operators in time, the same operators that we saw, that you see. And we're going to take a depth model of the very near surface. It's a very simple one. So you have the topography here. And so you have the air layer, of course. And just one single velocity, your first gauge velocity, which corresponds to the same velocity. Here, for example, 750 meters per second. And what we're going to do, we're going to try to stretch these operators that you see at the top in depth from the surface. So it's really taking these stresses on the top and stretch them to depth. And this is the image you can get. This is the image you have now. And the blue dashed line is the same, corresponds to the same reflections. So now, if I remove the colors, you see how in depth you are recovering the base of the dune and have a model of the dune base in depth along these receiver or source operators. On the right, it's just the outcrop of the hard layer, so you see reflection, but are not linked to the base of the dune. On another example, on the same survey, again, the receiver operators in time, and in depth, you have the base of the dune. And you see on the right also this dune. And on the source operator, the same thing. So in time to depth with a constant dune velocity model, and you can pick, so here the picking is not very accurate, but you can pick the base of the dune. Now, so we have migrated with one constant velocity. So the issue is that we don't know the velocity, as I said. So I will propose a few tools to help us decide which velocity is appropriate for this time to depth stretch. First, we can use, I think it's interesting, we can use two criteria, in fact. We could use the Hubble markers and try to minimize the misfit with the Hubble markers. In fact, it's another way of, rather than building up a strong constraint on the Hubbles, we're going to check the missile of the Hubble. So use the Hubbles more are a QC of the horizon, of the base of the dune. Here in this example, there is a zoom on a receiver deconvolution operator section. So it's a deconvolution operator. It's not it's multiples if you want. It's a multiple energy. It's not primary. So you can see the base, the topography, the base of the dune, and at this location we have a Hubble with in a yellow is a marker of the base of the dune, and you see that the seismic is above the base of the dune. The seismic is above the marker at the well. This tells us that the velocity that we have used for depth imaging is too low because we have stretched up the layer. So now we're going to do that for a range of velocities, 650, 700. You see there is a good tie. And if I increase the velocity, 750 meters per second, I go slightly below, and then 800 meters per second, and 850 meters per second. So 850 meters per second, for example, the seismic image is well below the upper marker. So this tells us that the velocity that we used is too high. And we can do that for every upper location. And from the upper location, we can display what we call, it's a classical depth imaging approach, mistime map for the different velocity scenarios. And here, the 700 meters per second velocity is a velocity that minimizes the misfits. So we can say that's the most appropriate velocity. And this is the velocity that we're going to use if you want to image in depth the base of the dune. You can tell me, and you're right, that it's not a perfect tie. There is a misfit, original misfit. And maybe, we have not done that on this project, but what could be done is to use a more sophisticated dune velocity model, like a competition velocity model, for example, to improve the well to seismic tide. So it can be an idea if you can derive a regional compaction law, then you can use this model to perform your time to depth stretch. Another approach is to look at the minimization, which doesn't depend on the hypothesis at all, at the minimization of the dune imprints. So you migrate in depth, and you're going to look at your base of dune and compute what I call a gradient, which is the structuration of your base of dune, and for a given velocity. And now if I compare the gradient of the base of dune with the gradient of the topography, you clearly, you clearly see that there is a strong imprint of the topography on my base of dunes. So this tells us that the velocity is not appropriate. And again, for the different velocity, you can look at this gradient. Here, for example, for a slightly higher velocity, you have the imprint is weaker. 700 meters per second, it almost disappears, and 750 meters per second also is very weak. But if you increase your velocity, you start to see again the imprint of the base of the dune. So by this method, we can select again. It's an example just to show how we can do. We select these velocities. So once you get the appropriate velocity, then of course you can migrate. You can use this velocity model to perform your depth modeling depth, and pick in 3D along the receiver line and the shot lines. So we are limited here by the acquisition box. If you have 250 meter by 300 meter, this is going to be your resolution. It's a kind of tartan of lines. That's why this method, I think, is very important, not to resolve the very short wavelength static, but to get the long wavelength static right. It is crucial in this method. It doesn't depend on any auxiliary data. And I will show you, so you compute, of course, the static, and you apply your static correction term. I will show you an example, the impact the impact of the technology used on the long wavelength static. So this was the first trial that we did, an initial model that we built on this project with a model from the interpolation of hopeballs. And you can see a cross line and an inline. Now you can see that there is a lot of undulation of the shallow reflectors, which tells us that maybe there is a static issue on this model. If I apply now the new model, computed from the surface consistent deconvolution operators, this is the change in the long wavelength imaging that I get. So I have a simplification of the long wavelength structure. Sorry? Okay, thank you. We have a simplification of the structure, and you can see that I have solved my medium to long wavelength static better with this model. And it has an impact, of course, on the, we are on the Elbama fault. It has an impact on the understanding of the structure of the deeper layers, of course. Just to conclude, to go a little bit beyond just the static correction, so we had, imagine a little deeper. We had a time to depth model with a constant velocity model. Now, what will happen if we migrate to a more sophisticated model by inserting a new velocity layer, hard velocity below? Now you will get this image. So going from one dune model to a new image in depth with a more realistic model. And you can see what is interesting, the folding that is happening to structure really the base of the dune. And if I compare that to a classical stack after regularization, you can see that on the stack, so on the primary reflection at the bottom, you don't see anything. On the image from decon operator, so if you want image from multiples, you get a high resolution image of the near surface. So this can help us interpret your very near surface. And if I compare him to a stack with depth migration, again, it's much better than a stack after depth migration, and you can see especially like a faulting, a conjugate fault around this near surface. Another example, another line, which is interesting because you can see a structured basement of the sand dune, which might help us understand the structure of the area. You can see that the dunes are formed just above where the fault is outcropping. So it can help us understand the geological history. And again, a comparison between primaries and multiples at the top. So as a conclusion, I presented you a new method to image the base of dunes, which is data-driven. This is important. I think this is the main advantage of the method. It works on a low signal-to-noise ratio data in any acquisition configuration, but of course the resolution of model will depend on the density of source and receiver that you have. It provides high resolution depth image of the base of the dunes, and it can generate a reliable, I think, a long wavelength static corrections. Thank you for your attention.
Ah, oui, chaîne 2.
Thank you very much. Preparation senior geophysics processing and acquisition specialist, holder of degree in geophysical engineering in Algeria University, with 24 years of experience. And he began his career at Sonatra for around 12 years and worked on processing application and various companies and as before worked for GeoX. And on different countries, Algeria, Egypt, Libya, Abu Dhabi, and France. Today he is the founder of director of the Geodata Services Company for oil and gas industry with a big interest.
Okay. No, it's okay, maybe less. Okay, good evening, bonsoir tout le monde. The presentation will talk about the key of element seismic reprocessing workflow with two examples in Waha zone. It was elaborated by myself and by Mr. Ashraf. As an introduction, as you know that the seismic data we use on the daily basis for well planning and investment decision should not be considered as a static resource. Continual improvement in seismic processing workflow, which creates the image we anticipate in support of billion-dollar investment decision year after year, required to consider seismic data as a dynamic resource, not as a static resource. So the exploitation of the old data can be one of the alternative to the new seismic acquisition. Knowing how the cost is a new acquisition, so the alternative can be that contribute to optimize the new acquisition program, so highlighting and extracting as much information possible from the old seismic lines is the most challenge. processing software have involved and can contribute to the improvement of quality by applying new process like PSTM or PSDM, but not only. So the improvement require an expertise and different philosophy of approach. So the best imaging improvement are achieved when the wealth of our workflow are built with attention paid to even the smallest details. This is really important. We don't have a miracle decision solution, but it's something like step by step with improvement at each step. So upgrading workflow to benefit from a series of small increment imaging improvement yields final image. So it's our expectation that improved imaging in achievable goals for every well-designed and executed seismic processing project. So the test, I mean the processing test was carried out on 2 seismic lines acquired in the 80s. They are very old lines, maybe 30 years ago, maybe plus. The first line was the 1130 part 123, 3 parts, and the second was the 642. The objective at that time, I mean in the 80s, was the TAGI located between 1.4 and 1.6 seconds. Currently, the objective are structural and stratigraphic between 1.4 and 1.6, of course, and the combo ordovation between 1.9 and 2.2. Note, this is very important. So the deliberate application of a conventional processing was intended to not highlight the software, but the approach of improving quality at each stage of the processing workflow. So the 2 lines tests are located in this area, which is Al-Waha permit. This is line 320 and this is line 642. This is the seismic line quality overview. This is line 321. As you can see, there is no resolution, maybe some continuities, of course, but we cannot see too much things if we are talking about resolution or stratigraphic element. This line is, in terms of quality, very bad. As we know that the target is around 1.5 and 2 seconds, you can see here we have nothing, and I don't think that interpreter can do something with this line. So the test objective was the enhancement of Triassic reservoir, enhancement of faulting, delineation of Triassic reservoir, amelioration of reservoir vertical resolution. Even if we know in the AT it's not easy to have some vertical resolution for sure. Just to have an idea about the acquisition parameters, it's quite similar. It's quite similar. The only difference is the fold. Here we have 430 and here 20, which means that we are in the very low fold. So the element that we received for the test, we got some field data in Segway format, 2D line TIFF, navigation coordinate, observer reports, static correction, and topography, elevation. So when we started the processing, knowing that the SPS doesn't exist at that time, so we need absolutely to generate the SPS from the old document. And this is one of the key to improve the quality. So before starting the processing itself, we can talk about the pre-processing, which is field document control, anomaly errors and issues, inventory, fixed problem, and then generating SPS from field doc, and then geometry creating, tools QC, and then starting the processing itself. So the problem difficulty faced, bad quality of field document with error, anomalies, and missing information, quality of writing, because most of them was at that time written by hand, lack of or no information remark on field document, bad scanning quality, conservation quality, etc., etc. Relating to the seismic data, low fold acquisition, noisy data, strong airwave, poor acquisition quality, very low ratio, signal on noise ratio. So this is an example of the document that we received. You can see this one is the good quality, this one medium quality, but even if you have something here, I don't know why they removed this value. As the line 320 was acquired in 3 parts, it was difficult to guess which is the first part, second part, and third part. And this is a document that you cannot use anymore. Another example of error that we found out is sometimes like this. We have a FFID number, which normally are production, and we have no information here, no remark. But when we display the shot, look at what we can see. This is, I don't know if it's test file or just noisy file anywhere, but still there, and there is no remark. Another series of FFID in the same case. They didn't mention any information, but they said that they are going for a break, casse-croûte, but nothing about the data itself. I think this is okay. It's enough as an error, but no, we have another errors. Like example of this one, this is test file, but if you look at the FFID, it's a production file, and there is no remark on it. I mean, the test file should be numbered from 900 to 99 at that time. Today is 999, 4 digits. But nothing mentioned, and they contabilized as a production file. Another error, which is really important, this is really a mistake, big mistake. Here we have 120 channels per shot, they mention, and if you look at the half spread, we have 60 in part and 160 in other part. This is absolutely unacceptable, and it means that there was no QC, nothing at that time, and there is no remarks. Other thing, navigation. If you look at here, in line 320, we have a value every 10 station, which could be maybe not a problem if our line is straight, so we can do a linear interpolation, no problem. If you look at this line, 401, 40, we have a random station, sometimes 20 station, sometimes 30, sometimes 15. Could be not a problem if the line is straight, but if you have a crooked line or a curved line, this is a problem. It's make a problem, and this is our case, because if you look at here, this line is straight, so we can do linear interpolation, but this is not the case. So we need to be very careful when we do the interpolation. The SPS file, when you fix all the problems, and this is one of the key of success, you need first to correct all the issues and anomalies and error in all documents, and then you can generate SPS file. Once we have the SPS, we can start the processing. So this is in summary all the problem that we faced with documents. It's too much for lines, but this is important to correct them if you wish to get some good quality at the end. Concerning the data, after you look at this data, we have some shot from the line. This one is very bad ratio signal on noise. Here we can see very strong airwave and some ground roll. The point is we started to imagine how to remove these airwaves. Is really, really hard to remove it. The first step that we did is just first to remove, or maybe to attenuate the airwaves. And the problem here, we're going to have to talk later on, that the previous processing, instead to attenuate the data, I mean the airwaves, sorry, they did a surgical mute. I mean, they remove everything here. So by doing this, they remove as well the signal, useful signal. So knowing that the fault is 20 or 30, I mean, there is nothing. So, and then we have removed the ground roll, or attenuated the ground roll. The same for the other lines. And to be sure that the signal is not affected by all these filters, we did a QC, and you can see here, no signal is affected. So maybe this is the second key to improve the data. as we know that the fold is very low, 20, we should preserve the signal, whatever you do. And then the first key is the first brick picking and the model to have good static correction. And this is, I think, the third and the last one with the good velocity at each step. This is really important. And then, so if you go now step by step, you can see this is the raw stack, and we can see some problems here. Static problems almost. And this is the stack with the FK for the ground roll attenuation. We still have, it's a little bit better, but still have some static problems. But after static application and the first pass, you can see here how the data is much better. The second pass, look at here, this Bowman, and here as well. So velocity statics can contribute to improve the quality. And this is with the stack with SVD, which is kind of a fixed decon for random noise attenuation. And starting from the beginner, we can get this quality. And if you look at the processing sequence, there is nothing special. We didn't put something new like PSTM or PSDM or TOP. No, nothing. We wanted just to keep a simple processing sequence just to see that starting from basic things, we can improve the quality. Okay. The only difference, big difference maybe, is the convolutions, as we use his DKC, deconvolution surface consistent, and with something for first break picking for the static, and of course with two pace. If you look at, it's not a big difference between those two processing sequence. So as the final result, this is the line 642. Remember that the target is here, and the second target is about 2 seconds. And this is the result. So now we can see that we can reach something here, which is the taggy, I believe the taggy. And here maybe at around 2, which is maybe the Combro Ordovician. This is a comparison between the old one and the new one. You can see how the new one we can follow some I think believe this is the Combro Ordovician, and here about 1.5 is the taggy. So you can see the difference between them. Of course, here we still have low frequency, but at least we have the continuity. Concerning the line 302 part 2, this is the old image, and this is the new one. As you can see the difference. For sure, you can talk about multiple for sure, but the aim wasn't to study the multiple for sure. The aim of this presentation is to see, starting from the documents and starting from the conventional processing sequence, we can improve the quality. Look at this one and look at this one. It looks like it's not the same section, but it's the same. And here you can see that we reached the target, which is about 2 seconds, and even more. I repeat, for sure, you can say that some multiple are there for sure, but it wasn't the aim of the goal of this presentation. The presentation is that we can see that actually extract the maximum information from the old data is a tedious job, of course. Maybe you need to spend a lot of time to correct all the documents. You cannot say we can do a big production because you need to spend much time. And the second thing is that you need to have a huge experience, because geophysicists less than 15 years, maybe they cannot understand what's happened at that time in the 80s, because the explorations have changed. And the main goal was to demonstrate, according with objective, the quality of the old seismic data can be improved by applying a processing sequence in adequacy with different type of noise, while talking about less basic points. Field documents free of error anomaly. This is the most important thing, because people used to start, but if the documents contain some anomalies, I prefer to talk about anomalies, not error, because to avoid to hurt any person or any company. Analyze and identify all the noise. This is really important, how to remove the noise or attenuate the noise with preserving the signal. This is really important. Apply the most efficient method in terms of static correction and prepare the data as the best possible for the migration step. Why? Because sometimes if you want to apply any PSTM, PSTM requires that about distribution of offset should be good, and some gaps are not really appreciated by the PSTM. So maybe we can apply some new modules like PSTM or to any something else. So it was a short presentation, but I think it's really important for company who has all data and think that we have to put it in the bin. No, we can always extract some extra information. This is really important. So thank you for us. If you have any question, that's it. Okay.
Thank you very much for this nice presentation. I think it's a lesson to learn, especially for young geophysicists who didn't have the chance to practice the processing actually. First of all, do you know that ETAP, who is organizing this EPC, has a processing seismic center 20 years ago working in the Khairuddin Bashar road? Do you know that?
I heard that a few days ago.
Okay. I was one of the former of that processing center at that time, and you got me back to 25 years when we were doing this kind of presentation, very simple, but focusing on the fact that déchiqueter in French, which is going to retrieve the information from the observed reports, is the most difficult part. Because if you don't do a good investigation of the history of your shooting, you don't have any chance to get good processing. And this is a key element, which is people needs to know now at the time for people who didn't practice. When you are asked to provide the field data, you have to go to find out if you have a complete data set of your field data first before the tapes. The tapes
Absolutely.
In general, they are damaged and sticky tapes. In addition to this, even if you are able to retrieve the data, you have a missing information like the SPS that you have to generate again, like the history of the shooting. The shooting is not regular. The difference between the offshore and the onshore, in the offshore the boat is running and the shooting is regular. You can generate your navigation by having the first shoot point and the last shoot point.
Exactly.
Supposing that the line is straight. In onshore, sometimes you have some obstacles during the shooting and people go and back, and if you don't document correctly all this history, you don't have any chance. And we have an experience on that. Of one of the line, which is the line TWT 9112 crossing Salem structure. TGVs could not provide realistic processing because of the lack of data spectrum also. The original processing is better because at that time they must have the maximum information that has been lost with time. So it means if you're not able to retrieve the all field information, you don't have any chance of onshore data to get the good processing. So thank you very much for this lesson.
You're welcome.
Especially for people who are facing this, or they are asked to provide data for reprocessing projects. Thank you.
I would like just to add one word. So process this type of line, probably for big processing center, is a problem because it's not profitable in terms of money, because we need to spend a lot of time to process. Not like a 3D, it's just computing, but this type of seismic line is a tidy job, really is tidy job, because you need to find out what's happened exactly and to explain. That's why I was talking about geophysics less than 10 years or 15 years, they cannot understand this type of acquisition. Exactly. You're welcome.
Presentation entitled Role of Seismic Imaging, Inversion Technology, and in Conventional and Unconventional Reservoir. Mr. Ali, I will present this. He's an experienced. He's an experienced geophysicist who has more than 35 years with the exploration and production sector. He occupied technical and managerial positions within various national and international companies, including ETAP Resources and Total, where he spent 10 years overseas. Since 2000, CDI acted as an independent consultant and gave several courses in engineering and training institutes. The floor is yours, Ali.
Thank you, Mr. Chairman. The title is Seismic Imaging Recent Breakthroughs in Conventional and Unconventional Reservoir Characterization. Well, the idea is to show how seismic developed since several decades, and both in conventional, but more recently also in unconventional reservoirs. So I will show you several examples from the conventional studies, and we'll focus more on unconventional reservoirs because in the future that will be the main play for exploration and development. Well, first of all, technology as a whole, the objectives of technology is to discover and produce hydrocarbons at affordable and economic cost, less than, of course, less than the oil price. And you keep in mind that majors pay a lot of attention to improve the technology, and they allocate 2 to 5% of their income to research and development, which represents billions of dollars. When you read some papers, scientific papers, for example, in the United States, you can see this type of information. According to the Energy Information Administration, the exploration success rate in the US onshore increased from 34 in 98 to 34.2 in 1998. Oh, that's the problem with the from 27.5 in 78. So in a few decades it has improved much. And they conclude that this increase can be attributed to the many advances in seismic and drilling technology that have occurred over the same period. Since its inception, so at the early 50s, seismic reflection technology has drastically evolved, and you can see it in any project management, be it, I think I have a better pointer because the, okay, sorry for the, yes, okay. So you can find it in any project management, from the design to the acquisition, processing, interpretation, and to the geological model and the simulation model for development and future production. So technology has evolved in these fields, and we have seen some example this afternoon at the different stages. Just to show some examples how this impacted the exploration and development, but also even the production.
have this example from offshore Brazil, which shows that what I wanted to show that until recent times only the subsalt and this section was explored, and this basin, the Santos Basin, has become a mature field. The reason for that is that below the salt, the seismic was unable to give an answer, and the image was very, very poor. But with the advances in seismic acquisition and processing, now the image is much better, and you can see here both different processing, but very recent processing. You can see that there is the base of the salt, and there is a large uniformity, but you can see also reflectors here, and in some places faults and so on. And this resulted in a new province, a new geological province, with the discovery of the 2P field, which is turned out to be a giant field. It has relaunched the exploration of the offshore Brazil. But the same thing also happened in West Africa and the Gulf of Mexico, a new area for exploration and new development. Also for stratigraphic traps, now more and more seismic data, if they are of good quality, can image also channels. You can see here we have an example of a channel which compares to surface channeling and meandering channel. And you can imagine that for exploration, but also for development and production, if you now have this type of images, you will optimize your development wells all along these channels instead of drilling them elsewhere where probably the reservoir is absent. This technology has not only improved the success rate in exploration, but also even in production, and you can monitor the production, what is simply called 4D or time-lapse seismic, where you shoot two seismic surveys separated in time 4 years or 10 years after your production. And this is an example which shows that, for example, here you have a small part of a seismic line which shows that very high amplitude on top of the reservoir where the field is oil bearing. This is geological cross-section, but after 5 years of production, the same survey shows that there is a change at the top of the reservoir. Here you have a high amplitude, but it's limited to this area, and in fact this is related to the change into the oil-water contact, and you only have this part, you have produced a large part of the oil, and this is what remains. So this will allow you not only to calculate your remaining reserves, but also to, in case of if it is favorable, you can better locate your wells for additional development. Yeah, some example from seismic attributes. Here is an example from the North Sea, where you have a seismic line, where it is very difficult to depict faults, except probably in this area, but all along this top of the reservoir it's very difficult to see. But using appropriate seismic attributes, you can see the complexity of the fault network. The same applies, and we will see that more closely in shale play development, where faulting and fractures are crucial for the productivity of wells. Another example from Tunisia, where you have just amplitude, the amplitude attribute, which was superimposed on a structural map. Not only you have a better definition of the faults, but also you can see that there are areas where you have what we can call direct hydrocarbon indicators, which are highlighted here in red and yellow. Two examples also from Tunisia. all of you know something about Ashtart and Miskar, which are respectively the largest offshore oil field and gas field. But what I wanted to show is that the discovery map, which was located the first Ashtart well, which was based on 2D data back in the early 70s, and after several years, the 3D data, and you can see the drastic change into the structural shape and the fault network. The same applies for Miskar. This is the discovery Miskar 1 well, and you can see the type of structure, gentle anticline with very few faults and so on. 3D data can change completely the picture, and of course this is very important for the reliable evaluation of gas in place or oil in place, but also for the location of the development wells. You will not drill into the faults, for example, here, and so these are some few examples, very quick examples, to show the importance of the and the impact of the development technology on this. Now we move to conventional and non-conventional and see some other technologies, including the 3D and microseismic acquisition. Just to remind what is called unconventional reservoirs, either tight reservoirs or shale formations now are beginning to be sound play, especially for shale reservoir. The difference with conventional is the quality of the reservoir, and especially the permeability. We have seen probably this morning a lot of presentations on tight reservoir, tight gas, which are less than 1 millidarcies, but more and more development of shale reservoirs, particularly in the United States, Canada, Argentina, have permeabilities in the macrodarcy, so very, very low permeability, which needs fracturing. And we'll see that seismic can help into evaluating the several aspects of the shale evaluation, and also and the productivity of the wells. This to show that in order to produce these reservoirs, you need to not only to have horizontal wells, but also to fracture that. And we'll see how the seismic can help in that. The best areas for evaluation of the shale plays, what are called sweet spots, several parameters should be rich in total organic carbon, more than 2%, type 2 kerosene, appropriate thermal maturity, thickness, more than 20 meters, porosity within the matrix and organic material, quartz carbonate and mineralogy, so that for this formation to be brittle, so they cannot break it and you can fracture it. But if it is, if there is not enough quartz or carbonates, it will be plastic and will not produce much from the well, and low saturation. I have underlined the areas where seismic can help, but I will focus on two of them, richness of total organic carbon, how we can determine that from seismic, and also how we can evaluate the brittleness of the rock. Well, all of you know how we acquire conventional seismic with a source on the surface, and then receivers also on the surface, and you can see, for example, the high resolution of this seismic section all along Eagle Ford shale in the United States. Not only you can identify the main faults, but also you can see even fractures fracturing that, and you can follow. This is the main reservoir, so this can help to properly locate your wells and your objectives. But now what is called microseismic, instead of listening to from the waves propagating the waves, we will listen to the fracture. because as I told you, we need to fracture all this, but how to monitor that and how to be aware that we have done the best job of fracturing. So when we listen to the fracture, you know, when you break a pen or whatever, you say you hear a sound. So this sound is recorded on the surface or in a monitoring well, and you can pinpoint the position of this fracture. This is a schematic cross-section where you can see the location of the well path, the horizontal section, but here is color-coded the different fractures which have been undertaken, and this area has not been fractured yet, but you can see that your fractures are well positioned within the main shale and did not propagate to the surface as many fear, and you can see if you have properly fractured your zone. So this is very important to monitor what you are doing, so that not to be first of all away from large faults, so that not to rejuvenate them when you fracture the formation, but also to pinpoint exactly where you have done, if you have done a good job and where you have done it. Okay, now we come to a more recent technique called seismic inversion. 2 minutes. It's 20 minutes plus 5 for discussion, right? It's not 15. I've heard you saying it's 15 minutes. Okay, sorry. Okay, I will be quick. So what's an inversion? An inversion is an attempt to predict rock properties, porosity, thickness, fluid content, hydrocarbon saturation from seismic data. There are different types of acoustic impedances, and here you have acoustic impedance, elastic impedance attributes, and what you can get from them, mainly porosity, thickness, lithology, and water saturation. So I will show you some of these examples. Well, don't have time for the theory. In fact, the reflection strength as a function of angle of reflection are dependent on the density, velocity, compressional velocity, and shear velocity. And these, the inversion theory can allow to get these elements, P impedance, shear impedance, and density. And these in turn can give elastic parameters. So instead of we make different collections of seismic data, instead of stacking or adding all the traces from a survey, we subdivide them in near traces, middle traces, and far traces. This is one example in Tunisia where we have 3 seismic cubes instead of 1, and you can see there is an avia effect. That means that the amplitude changes from the near offset to the far offset, and this is used in the inversion to come up with the acoustic impedance, compressional, and then extract some elastic parameters. This is the relationship between the elastic parameters, mainly 2 parameters, lambda and mu. Lambda is an indicator of pore fluid. So if there are hydrocarbons, it will affect lambda. And mu is for the matrix. So it gives the lithology of the formation. Well, this is a quick example from the North Sea, Heimdal field, where they pretty well identify the structural aspect, but when they drill this feature, the reserve is chalky limestone, and the porosity is variable and very high, generally very high. But when the porosity is low, they have, even within the structural aspect, they don't find hydrocarbons, right? And they have tried to see if the seismic can help with that. And there is a correlation between acoustic impedance and porosity. So they said, okay, we will transform our seismic into an acoustic impedance and then into porosity element. And this is the map. In yellow, the most porous area, and probably you don't see it from far away, but here they have shown the structural map. So there you see there is no coincidence, not exactly the coincidence between structural aspect and the porosity distribution. And it's the reason why this type of wells are negative, whereas those ones in the blue section, so future wells were drilled all along this porosity, high porosity area, even if it is outside the structure. So this is a combined structural and stratigraphic trap where seismic, the acoustic impedance played an important role. This is an example from Tunisia where we have identified the acoustic, the elastic parameters, and lambda, for example, mu, which is shows the lithology. You can see the it's a shaly and sandy reservoir. So the best reservoirs are in blue, in yellow and red, and you can see its distribution in this area. But also the other elastic parameters, lambda rho, can show that the water saturation, and of course this is the hydrocarbon saturation area, and you can see in the same, the best reservoir also holds the best content of gas and oil. The same inversion was used to determine the richness in total organic carbon. This is the seismic line, and its inversion into terms of acoustic impedance. And this is there is a close relationship between acoustic impedance and the content of carbon organic total. And you can see that the best areas are located at the top, but within the reservoir, the rest of the area is there is some heterogeneity, and this allowed to better locate the future wells. Last parameter, the brittleness, how the rock can break, and this is also extracted from two parameters called Poisson ratio and Young modulus. There are some equations for that. And here again, we go through the inversion, and this is the compressional acoustic impedance, and the main reservoir is here. It's the lowest acoustic impedance. For the shear wave, acoustic impedance, the same. From this, they have extracted these elastic parameters, the Poisson ratio and modulus, and those ones can allow to compute the brittleness and the best areas in red and yellow. And you can see the main reservoir is this, but you can see that a lot of heterogeneity. It's not a homogeneous reservoir here. In blue, really very shaly zones which will not break. So if you drill your well in this area, you will not get enough production. And they can even calculate the percentage of sand within this reservoir. The last slide, the position of the wells prior to doing this job for brittleness. You can see that the horizontal section here is not really positioned in the best zone, which is in red here. Whereas when they have performed this work, you can see that the well now is well positioned in the most brittle and zone. And here you have some figures to show that the production has increased 2 or 3 folds when they have used this technique. Also, you can see at the base there is a lot of ductile shale. So when they break the formation here, it will not propagate into the lower section. And this brings me to the conclusions. So technology and innovation are indeed the driving factors for the development of conventional and unconventional reservoirs and hydrocarbons. They are necessary to provide the world with the necessary oil and gas resources at an affordable and economic cost. Seismic technology played an important role in this respect and largely contributed to not only to the improvement of the success rate at the exploration stage, but now constitutes an important milestone in the development and monitoring of oil and gas fields and production. More recently, seismic inversion technology largely contribute to a better and more robust reservoir characterization and a better productivity from both conventional and unconventional reservoirs. They are used to unravel unconventional reserves from the hydrocarbon rich Silurian and Devonian formation in southern Tunisia and North Africa shales can offer huge economic potential for the future exploration and development of these shales. Thank you for your attention.
Thank you, sir.
مرحبا. I think this one. That's good. Thank you for the show.
Yes, I'm good.
نقعد ناكل هوني انا ما عندي منام اللي يجيني النوم ما كنقدرش لهذيك والله يعني طعم
الطفل اللي جنبي يعمل يوم كل عبنا لي جوا من انستغرام
تربح ولا تخسر
عادي يجي كلنا نوريك ليش تبع فيسبوك
Can we start? Okay, good afternoon, everybody. I'm really happy and honored to chair this session. And for that, I would like to thank the organizing committee, especially ETAP, for giving me this honor. So for this session, we have 4 topics. We'll talk first of all about the water project, which is the main gas project in the country that we are doing. And after that, we'll go to another challenging project, which is done in the Sfax region of the pipeline crossing Sfax town. So, and 2 topics about new technology, talking about the home assistant technology production in the field, and electromagnetic reservoir mapping by the. So we will go to the first presentation, which will be, we'll talk about the Wara gas project, and it will be presented by 2 gentlemen from ETAP, which is Walid Abbas and Nassim. Okay. So Walid Abbas was graduated from National Institute of Science in SAT and applied technology in chemical industry. Then he got master's degree in petroleum engineering from National Engineers School of Tunis in it. When he started his professional career in Pioneer, then he moved to British Gas, Tunisia, during the commissioning of Asdrubal gas plant as a junior process engineer. For the STGP, in 2010, he has been effective as process engineer for the STGP of Nawara and integrated for ETAP URBT. Then at PLI headquartered in Milano, San Donato, as step-by-step passed on GTP and nice kind of appetizer yesterday. So let's talk about now in detail about our project.
Good afternoon to everyone. Thank you for being here. So today I will present Nawara project, which is one of the most important and strategic project in execution phase. So we have two parts. The first part is about the upstream package of the project from the well sites to the CPF, and the second part is from the export line to the GTP. The gas plant GEPS will be presented by my colleague Walid Nabez. So this afternoon we will see the history of Nawara project, the permit, the concession, and the location of Nawara. We will talk about the reserves and the production plateau. We will see also the different components of the project, from the well sites to the export lines to the facility. We will see the surface facilities of Nawara, the current status, the situation now, and of course we will conclude by seeing the benefit of this strategic project to Tunisia, represented by ETAP and our partner OMV. So Nawara project is located in the extreme south of Tunisia, in the governorate of Tataouine. It is part of Jnaïd Sud permit. The discovery was in 2006. Nawara well, which is a gas and condensate well, was discovered in this region. So the concession was granted to ETAP, representing Tunisia and our partner OMV in 2010 for a duration of 30 years. The area is around 528 kilometers, and as I said, it is in the extreme south of Tunisia, so the geography of this region is mainly desert, so sand dunes and some rocky areas. So here is one of the most challenging aspects of the project, mainly for logistic and construction activities. The reserves of Nawara. So Nawara is a gas and condensate field. We have reserves of around 10 billion cubic meters of gas and 7.1 million barrel of condensate. So this represents a total reserves of 64 million barrel oil equivalent. This reserve is will have a gas production plateau of around 15 years at a flow rate of 2 million standard cubic meter of gas per day, and 3 years of 5,000 barrel of condensate per day, which is quite important for both Tunisia and OMV. In the future, there are wells planned for the improvement of the production. So the main components of Nawara are the CPF and the upstream part. So we have 9 wells. We have a gathering system which is individual flow lines from the well sites to the main treatment facility. So the CPF, which is located near Nawara well, this plant is for the treatment of the gas and condensate before the export to Tatawin plant and Gebis for the final treatment of the gas, and to Trabza for the condensate production. So I will focus on the first section, which is the well sites, the flow lines, and the central processing facility. So in the well sites, we have the well heads. We have solar panels for power generation, which is needed for the chemical injection pumps and the control panel of the wells. We have a data transmission system for the data transfer from the well sites to the CPF, the flow rates, the pressure, the temperature, all needed data for the production and maintenance activities. The gathering system is individual flow lines from the well sites to the CPF. So we have 6-inch flow lines from the 9 well sites to the CPF. The central processing facility is, as I said, for the treatment of the gas, the condensate, and the produced water. So we have test and production separators. We have condensate stabilization unit to remove the gas from the condensate. We have off-gas compressors to recover the flashed gas from the treatment of the stabilization of the condensate. And we have a storage tanks, 2 storage tanks of a total capacity of 20,000 barrels. This is for the final storage of the condensate before export to Trabza pipeline. Of course, the metering is a fiscal type metering, Coriolis type. This is upstream the export line to Trabza pipeline. For the gas train, we have sweetening to remove the CO2 from the gas using amine technology. We have dehydration package using glycol to remove the vapor, the water vapor from the gas. We have hydrocarbon dew point control unit. So this is to remove the liquid fraction from the gas. So we use the refrigeration cycle technology. We have propane refrigeration package, compressors, in order to meet this hydrocarbon dew point specification. For the metering, as the condensate, it's a fiscal type using orifice type. Before export of the gas to both Tatawin plant and Gebis treatment for the final treatment of the gas. The water will be treated in the CPF as well, and the produced water will be treated. Produced water will be sent to evaporation ponds in the desert near the CPF. We have as well all needed utilities, the chemicals, the nitrogen generation, the power generation, because as you know, we are in the middle of the desert, so we need the standalone power supply. So we have 2 gas turbines for the power generation of a total capacity of around 6 megawatt. All these units will be fully automated. So we have integrated control and safety system, process control system, emergency shutdown for the emergency case, and fire and gas detectors connected with the firefighting system for emergency situation. So this plant is fully automated with a control system and a safety system in the control room. Regarding the design capacity of the CPF, for the gas train, it's 2.7 standard cubic meter per day. This is the current facility, but in the future we can add the future train and other equipment. And for the condensate, we have a design capacity of 7,000 barrels per day, which is based on the reserves we have now and the sales agreement we have with STEC and with Trapsa. The current situation. So now we are at the completion of the construction phase. So all engineering, procurement and manufacturing phase is completed. So we have all the studies needed, all the equipment are on site. The progress of the construction is around 75%. The civil and structural works, which include the foundation, the pipe rack, the structured steel, is almost completed, 90%. The installation of the packages and the mechanical equipment is also almost completed, around 95%. So now the main activities we are focusing on are the piping, linking the different equipment with a progress of 70%, and the cables, the control cables, the electrical cables, which is also the main activity during the upcoming months. So it's a progress of 40%. As you know, before the introduction of the gas, we need to test each piece of equipment in the CPF. So this is the mechanical completion and the pre-commissioning. We already started the test, and we have a progress of 6%. After the completion of this phase, we can start the commissioning. That means the startup of the different utilities before the introduction of the first gas, which is planned in 2019. So to summarize, we are at the completion phase, and the target is to test the equipment, the units, and all the package, and to introduce the first gas in 2019. So to summarize, as I said, Nawara is one of the most important and strategic projects now in Tunisia. The benefits of this project is, of course, the job creation during both construction and operation phase. During construction, we can reach 1,000 direct jobs, plus, of course, the indirect jobs, mainly in Tatooine region. During the operation phase, we have around 100 direct jobs for operation and maintenance team, all support jobs like the administration, the security, the catering, etc. Plus, of course, the indirect jobs in the region, mainly in Tatooine. This operation phase is planned to last 25 years. This, the financial benefit, of course, is it's the second benefit of Nawara for both Tunisia, represented by ETAP, and our partner OMV. So with this production of gas and condensate, Tunisia will improve its gas production. Also OMV, our partner. This gas production, it represents around 15% of the total national gas consumption, which is as you can see, quite important. Finally, we have the pipeline from the CPF to Gibbs, which is future infrastructure for all the concessions of gas in south of Tunisia. It's a 24-inch pipeline with a capacity of 10 million standard cubic meter per day, so it can export not only Nawara but also the future development project in south of Tunisia. So here we can see some photos on site. This is, for example, Khulud wellhead. You can see it's in the middle of the desert, so we can see the sand dunes. This is one of the well sites. So we have 100% photovoltaic panels for power generation. This is for the 9 well sites. This is the central processing facility. So you can see for example, this tank is for methanol, and we can see the pumps and all the utilities. We have a corrosion inhibitor, we have demulsifier, all the needed chemicals. This is the process train with the hydrocarbon dew point unit. Here we can see the propane compressors for the refrigeration unit. This is also the CPF as it is now in the current situation. So we have the hot oil. This is the furnace for the hot oil needed for the processing of the gas and condensate. We have, as I said, 2 gas turbines of a total capacity of 6 megawatt. So here we can see the 2 gas turbines in the CPF. We have 2 tanks for condensate storage, a total capacity of 20,000 barrel, 4 days production. This is the high pressure and low pressure flare stack. So before moving to the downstream part of the project, which is the export pipeline and the gas treatment plant in Gibbs, thank you for your attendance, and if you have any questions or clarifications, you're welcome.
Construction of the CPF, 75%. Of the construction, 75%.
So the construction progress is calculated on the different discipline progress. For example, here, yes, so 75%, it is the total of the civil and structural work, which is 90%. Of course, we have the weight of each discipline. We have the mechanical installation progress, 90%, the piping installation, and the control, instrumentation, and electrical progress. So we have
weight of each item.
We have a work breakdown structure, and based on the man-hour of each activity, we have the total progress of construction activity. Do you have other questions?
My name is Bilal Neifer. First of all, thank you for the detailed presentation. My question is, when do you expect to start the project? When do you expect to start producing gas and gas treatment, etc.?
So, as I said, the commissioning and startup is planned in 2019. So now we are at the completion phase. So before the introduction of first gas, we need to test and check all the equipment, all the cables, each part of the project facility. So of course here, it depends on many factors, like the social stability, like the performance of the subcontractors. But the plan is to commission, to test, and the startup in 2019.
Yeah, I mean, so it will be in the first quarter, second, third, or fourth quarter?
Now it is planned in, I think it's in middle of 2019. But as I said, this is depending on many factors, like the stability of the region, the performance of the subcontractors. Of course, we have sometimes some surprises or some, but this is the plan now, mid of 2019.
Okay.
So this time, Seat Wahab is here. So this is what it was also said by all the media today. Do you confirm, Seat Wahab? Yeah, okay. So means that by end of June 2019, the gas will flow to gas and to the network.
Maybe I can add some clarification which may answer certain concerns. So the total progress of Nawara project is exceeding now 90%, we are at 91, 92. This if we consider three components of the project, but if we consider only the CPF, yes, the construction till end of September we are at 77, 78. I can come back to the question of colleague Salim about how we estimate the wave. So there is a baseline and there is a wave of its activity and there is a planner who follow up the activity. So it is monthly done how we calculate the progress and whether it is 70 or 90 or whatever. For the delivery of Nawara, normally now the date schedule it is, the latest updated schedule. So mechanical completion will be January 15th, January 2019, with the ready for startup. It will be end of April, May. But when we say the contractor delay June or July 2019, this is for the PAC, the provisional acceptance certificate, which is normally 1 month after performing the performance test. Okay. So let's be now optimistic and consider that we will receive Nawara gas middle of 2019. But the third part, or let's say second and third part of Nawara project, will be commissioned soon and we will be able to use them for other processes like Edom gas. So the target now is to start first quarter producing Edom gas through Nawara assets. Thank you.
Next, any more questions? So let's take maximum 2 questions, otherwise we are a little bit late.
شكرا شيبوب subsurface team leader for shared Diffusion.
I mean, we are all working in the same thing. So it's good to be all here in the Nawara project, seeing the lights. So it's very good for the country, for the foreign investors. My question is taking into account the large expenditure around this project. Is there any upside around this project? I mean, what you have showed is probably your base case scenario. What's the upside of this project? Are there any other upsides to it?
The future
yeah,
installation.
I know within the reservoir, within your accumulation, is there a potential upside that could potentially materialize?
So this project is
So maybe should be able to just make some precision. So your question is about upside. So this is the potential of the region, yeah? So this means that now we are developing a cactus reservoir. So most of the structure were drilled by single well, and the most important upside is as you know, is the automation there. So the pipeline is big enough to drain all what will be discovered in the future, what it will be developed in the future, and I don't know, Siali Guy here is one of the people which is defending this shale gas. It will come one day. So the pipeline is there, infrastructure is built. You are welcome to produce and to bring together what it will be discovered. Not now.
I just want to clarify one point. We expect to produce 5,000 barrels of condensate. Yes. And the storage capacity is only 20,000 barrels. You think it's enough for such a project?
It's based on 4 days production, which is a peak. It's not during a long period. This is based on the design of the storage tanks was based on the maximum capacity of condensate production, and the plateau is only 3 years. It's not like the gas, which is a long plateau of 15 years. So we based on 4 days production, and this is the maximum capacity.
Last one.
As for the level of pressure in the transmission of the pipe. Pressure. Maximum pressure for transmission in the pipe.
The design pressure of the export pipeline. Yes. It's 111 bar. This is the pressure. And the capacity is 10 million standard cubic meter of gas per day. 111. Because it's an infrastructure. It's not only for Nawara, but it's also for the future development in the south of Tunisia.
I want to thank you for your valuable presentation. We just, I think that the two gentlemen, they made it a kind of applause. Thank you. Very. Okay, so.
Thank you, Wasim, for the presentation. So I will continue the presentation of the Nawara. So two major other components of the Nawara project is the pipeline and the GTP. So I will start with the pipeline. I will present, this is the agenda of the pipeline. So I will show you an overview of the project, pipeline configuration, pipeline equipment, the 24-inch main pipeline configuration. This is the operation of the pipeline, some photo galleries, and the current status of the pipeline. For the second part is related to the gas treatment plant in Gabis. I will start with introduction, GTP units. We present the block flow diagram of the GTP, units description, process flow diagram, it will be a very basic one, GTP mode of operation, some photo galleries, and GTP current situation. So this is the map of the pipeline. In total, we have 10 pipelines, without considering the flow lines from the wellheads to the CPF. So this is the main pipeline, 24-inch feeding gas from CPF to pipeline. We have two feeders now for the Eli gas scenario from Waha and ENI. We have a withdrawal of gas of 0.6 million from Nawara to TGP gas project, 12-inch. At GTP site in Gabis, we have 5 pipelines, 1 dedicated for the sales gas, 2 for propane and butane, 1 for the stabilized condensate, and 1 pipeline to import gas from STEC to GTP for the hot commissioning phase. Okay, I will skip this. This is not very important. Okay, so for the equipment of the pipelines, we have, as I said, 5 pipelines in GTP. Sorry, 10 pipelines. 1 main gas from CPF. We have 2. Sorry, this is from. This is the stabilized condensate from CPF to TRAPSA, main pipeline, intermediate pig receiver and lasher. At GTP, we have propane, butane, condensate, and buyback gas. We have pig traps, pig lasher and receivers. We have mobile flares for depressurization. We have HIPs. We have electrical heater. I will show you later on why you are using the HIPs and the electrical heater. Metering skid for the sales guys, propane, butane, and stabilized condensate. This is the 24-inch pipeline. So the gas 24-inch pipeline. Yes, we have 12 long valve stations used during leakage. Each one is have an SDV for emergency case. So normally the gas is fed from CPF, flowing this path, bypassing the intermediate big receiver and lasher, going to GTP, to slack catcher of the GTP. At each valve station we have a connection for mobile flare and a connection for future connection just in case one connection want to feed the gas into Nawara pipeline. So now I will talk about some data operation system. So the 24-inch pipeline conveys natural gas in gas condition phase. Each concession is responsible for supplying the requirement nominal flow. The delivery pressure at GTP inlet shall be 35 bar. Each pipeline segment can be pressurized through the mobile flare, as I said before. There is a 12-inch Tatawin gas pipeline connected between LVS 7 and 8 for Nawara, for the Tatawin gas project. For the condensate at CPF, so pipeline conveys condensate at liquid condition. Delivery pressure depends on the back pressure, of course, at TRAPSA site. The pipeline is equipped with pig lasher and receiver. For at GTP site, we have sales gas pipeline. The pressure floating normally between 16 and 75 bar. The fiscal metering is present at STEC. It is an orifice technology. HIPS package is located downstream of the fiscal meter to protect the STEC pipeline from overpressure. For the propane, we have pipeline conveys propane in liquid phase. The PCV to regulate the pressure at the setting pressure of the storage. We have big launch and receiver, fiscometer, of course, Coriolis, and HIP system located downstream of the fiscometer to protect the STP storage for overpressure from GTP pumping station. The same thing for the butane, the same configuration. We have 6-inch bypass gas to import gas from stack to GTP for the hot commissioning phase. Pressure is 35 bar. We have here electrical heater just to guarantee the minimum delivered pressure by the GTP conductor, which is minimum 10. The pipeline is not equipped with big launch and receiver. We have a flow measurement, but not fiscal. And we have a connection for mobile flare for depressurization. This is the new pipeline for the condensate, stabilized condensate. We have pump to export the condensate, stabilized condensate from GTP to stack LPG plant. There is no big launch and receiver. No requirement for depressurization in this case. So coming here for the line valve station. So here some equipment. I took the example here for the Trapsa. We have passive coulter shelter, photovoltaic, battery charger, batteries, lighting system, earthing, cathode protection. And this is the after 3D model. For the GTP receiving, particularly the same configuration. In this case, we have passive coulter shelter, electrical parts, normal power supply from GTP, UPS from GTP, earthing system. This is after 3D model review. GTP launching, this is the same configuration, passive coulter shelter. This is after modelization. This is SNDP, active shooter. Normal power supply from SNDP, UPS, lighting, earthing. This is after 3D. Here are some photo galleries for the mobile flare package will be used at Oxport and the main pipeline. This is a typical mobile flare. Photovoltaic panel for energy, knockout drum, elevator system, flare riser, connection. Some other photo galleries for this is the LVS 3 or 4, I forgot. This is the one of the LVS during construction, and this is batteries. I will finish by showing the pipeline overall progress figure. So we are at detail design. It is 96 pending. This is basically as-built drawing. Procurement 100%, subcontracting service 100%. Now, right now we have 90% construction. Commissioning startup 31. The overall is 97.85. I will continue the GTP then if you have questions. The Nawara GTP gas treatment plant is located in Gabes. The GTP will produce sales gas, propane, butane, stabilized condensate. The design capacity is 2.7 million. We expect to produce 2.45 million standard cubic meter of sales gas. Produce propane, maximum 210 tons. Butane, 120. Pentane is the side product. Stabilized condensate is 220 barrels per day. This is the latest Google map of the GTP. So that you have here the main entrance. We have contractor camp, company camp, operation camp, storage area, and this is the gas treatment plant. So GTP consists of the following tiers area. We have big traps, slack catcher, booster compressor, dehydration and mercury removal unit, LPG recovery unit, separation of the LPG, sales gas compressor, propane and butane storage, condensate storage. This is a block flow diagram. So you have inlet separation. You have booster compressor to boost the gas from 35 to 67 bar, dehydration unit, dew pointing unit. These are basically gas. As you saw here, gas is in green, the liquid is in blue. So the producer gas is boosted by sales compressor to stack. This is the overall recycle. After dehydration, after refrigeration through the turbo expander, we produce liquid. It will be fractionated. We will produce at the end propane, butane, and stabilized condensate. So this is more detailed description of the units. You have unit 220, so equipped with slackacher with any free liquid from pipeline and water are separated into hydrocarbon gas. Booster compressor designed to compress gas up to 67 bar gauge. Gas dehydration unit, this is a molecular sieve technology. We have dew pointing unit, unit 130. Unit 233, this is the sales gas compressor. 216, it is the fractionation unit. This is basically de-ethanizer, depropanizer, and debutanizer, and depentanizer. We have a storage facility for the propane and butane. So for the LPG products, so we have pressurized storage bullets with transfer pumps. The storage is 3 days. The export pump spheric storage tank, one dedicated for the on-spec and one dedicated, sorry? Ah, okay, sorry. Pentane, we have one bullet. Storage capacity 5 days. Utilities, this is a typical utilities in gas plants. Heat medium, fuel gas, flare system utility, open drain, closed drain, diesel, air system, nitrogen, power generation, emergency power generation. This is a very simplistic process flow diagram. This is a pig receiver, slackacher, booster compressor, dehydration unit, cold box, absorber and ethanizer recycle mode to produce the sales gas, depropanizer, debutanizer, depentanizer, 5 storage for the propane, 4 for the on-spec and 1 dedicated for the off-spec, 3 for the butane, 1 dedicated for the off-spec and 2 for the off-spec. For the condensate, we have 1 on-spec and 1 off-spec, and this is the pentane. The GTP operation, we have 2 modes. We have the turbo expander and the G2 mode. The design capacity is 2.7, turn down is 0.6. Some photo galleries, this is the slackacher. This is booster and sales gas, 2 booster, 2 sales. Molecular sieves. This is the tower, and here switching valves. Dew pointing unit, absorber, ethanizer. This is the turbo expander, and this is the lube oil of the turbo expander. Power generation. The propanizer, the butanizer, and the depentanizer. Storage bullets. This is 1 year ago. This is last week picture. This is the control room, opening directly to the field. This is the PSV and the blowdown valve platforms, 3rd level of GTP. And this is the overall picture of the GTP. We'll finish with the current states of the GTP. So the cumulative overall progress is 97.82. Permanent construction is 99%, pre-commissioning 18%, commissioning progress is 66%. This is compared to the October baseline of 2017. Thank you very much.
Thank you very much, sir. Ladies and gentlemen, good afternoon, and thank you very much for your presence today to this presentation. Today I am coming from SFAX, from TPS, to present to you a challenging project, a project made by Tunisian brain and hands. It's called GBIBA Tank Battery CFTP Pipeline Project. So the agenda of our presentation is the following. We'll start quickly by presentation of TPS for who don't know TPS. After that, we will talk about the pipeline project. We'll talk about the background of this project. We will give some key informations, the design basis, the scope of the project. We will see together the flow diagram. And after that, we'll talk briefly about the challenges and the opportunities offered by this project. So let's move to our presentation. For who don't know TPS, TPS is Tina Petroleum Services. It's a service company, a joint venture between the Tunisian NOC, National Oil Company, ETAP, and the Austrian oil company, OMV. It started activities in 1992. TPS is located in Sfax region, to the south. TPS is operating 5 small oil fields, 4 onshore, which are El Ain, Rimura, Gbiba, and Al Hajr, and 1 offshore, which is Sersina, near Kirkena Island. The average daily production of TPS is about 5,000 barrels of oil, associated to 12,000 barrels of production water, and 1.6 million standard cubic feet of gas. This is briefly TPS. TPS is operating in the midtown of Sfax. Sfax is the second biggest town in Tunisia. So here you can see the houses, the facilities, and TPS is operating in the midtown of Sfax, in a radius of about 25 kilometers. Here you can see the different sites of TPS, located in the midtown of Sfax. Since we have not a lot of time, so I will not read all this, what is written. And anyway, TPS is activities are located in urban areas in Sfax downtime, which causes huge challenges to operate. The produced fluids by TPS from well sites are carried by flow lines to 2 central processing facilities, CPFs, which are Gbiba station and tank battery. We will see them, Gbiba station and tank battery, later on when we present the pipeline project. All these produced fluid are separated into elementary phases, which are gas, oil, and water at Gbiba station and tank battery. The gas currently is used for power generation and excess is flared. The water is injected back in the reservoir or in disposal wells. And the stabilized crude oil is transferred to Trapsa, which is the sale point. Now we will move to our main topic today, which is Gbiba Tank Battery CFTP pipeline. Since the beginning of TPS, the startup of TPS in 1992, the crude oil after stabilization was transported by road tankers. So you can imagine road tankers are crossing the main roads of Sfax, full of crude oil, to transport this crude oil to CFTP or to Trapsa. This is very risky. After 2012, 2011 especially, after 2011, after revolution, mainly social events and safety reasons led to the decision to avoid trucking and build a permanent infrastructure for oil transportation. The main factors who led to this decision are continuous increase of road tankers fees, especially after this revolution, and degradation of service quality, limited flexibility due to limitation of transportation companies, means unavailability of tracking services due to social problems, sit-ins, all this stuff, and especially we have high risks and safety issues associated to road tankers, like road incidents, overturns, fires, explosion, etc. All these factors led to take the decision to build a pipeline to stop trucking of crude oil from TPS CPF. So in 2013, TPS and its shareholders, ETAP and OMV, took the decision to invest into a crude oil pipeline connecting TPS Biba station and tank battery site to CFTP CPF. CFTP is a company from Tunisian petrol. This company owns an old pipeline which is connecting CFTP CPF to Trapsa. The project, I mean the pipeline project of TPS, was awarded to a consortium of 2 Tunisian contractors in September 2015. And the contractual duration was initially 10 months. So this project was initially planned to be completed after 10 months. Here, the main key informations about our project. The project name is Gbiba Tank Battery CFTP Pipeline. The contractors who made the engineering, procurement, construction, installation of this project are IAC and PGS. Both of them are from Tunisia. The engineering subcontractor is Alpha Engineering, the Tunisian engineering company also. The review, approval, and supervision of all the work was done by TPS and its shareholders, ETAP and OMV, of course. The contract signature was in September 1st, 2015. The contractual duration was initially 10 months. Unfortunately, the project was not completed after 10 months. It was completed after about 2 years, and the put in service date was December 8th, 2017. So now the project is running and the target was reached. Here a map, simple map, showing the road, the pipeline road. As I told you before, here is the midtown of Sfax. You can imagine here there is plenty of houses, plenty of infrastructures, of roads, and the pipeline came from Gbiba station, is laid down from Gbiba station, crossing a lot of roads, one highway, main roads also. It's coming from Gbiba station for a distance of 13 kilometers to tank battery, and after that, from tank battery to CFTP. And at CFTP, we are connecting to an old pipeline going to the Trapsa at La Sfera town. So this is our new project shown in yellow. The total length of this pipeline is about 35 kilometers. We will see now the design basis of this pipeline. So this pipeline was designed for a flow rate of 15,000 barrels per day, which is approximately 100 cubic meter per hour of oil. The design pressure is 80 bars. It was hydro-tested to 100 bars. The pipeline diameter and length, the pipeline diameter is 8 inch, and the length is 35 kilometers. The material is carbon steel EPI 5RX42, 8 millimeters, schedule 40. And the design of this pipeline was done according to national and international standards, mainly NT 100 B31.992 ASME B31.4 and all other international standards. During this project, what was done is a laying down of an 8-inch by 35 kilometers underground pipeline from Gbiba station to tank battery, then from tank battery to CFTP. This is the main challenge. The construction of this project was really a challenge because it was crossing a lot of communities, a lot of towns, a lot of small cities. Also, within this project, we installed 2 pumping stations, fully instrumented with all accessories like metering skids, chemical injection skids, peak traps, process safety control, fire and gas detection system. All this stuff was installed within this project. And within this project also, we did the upgrade of our oil transfer facilities at CFTP, and we installed more powerful export pumps to export the oil from CFTP to La Trapsa. Here, simple, very simple and basic flow diagram of the pipeline. I think this is the main important slide. Within this project, we built a new pumping station with facilities at the Gbiba station. We laid down a 13-kilometer pipeline, 8-inch pipeline from Gbiba station to tank battery to transport the crude oil from Gbiba station to tank battery. After that, we built also a pumping station at tank battery. The oil from Gbiba is mixed with the oil from tank battery and pumped to CFTP, the delivery point, through 22 kilometers by 8-inch diameter pipeline. Also within this project, we installed more powerful pumping station at CFTP. So here, generally, what was installed within this pipeline project. Okay, thank you. So here we can see, as I started my presentation, this is a project made by Tunisian brains and hands. All the engineering studies, design review, ASOP, specification, procurement, all this stuff, construction, installation, pre-commissioning, commissioning, startup, and project management was done by Tunisian competencies, by the contractors and by TPS and its shareholders, ETAP CHAINE2. The new pipeline, also second challenge done during this project, the new pipeline crossed highly populated area in Sfax. You can imagine there is a lot of roads, a lot of cities crossed by this pipeline, and you can imagine the CSR issues we encountered during the construction phase. It is clear we did some delay to deliver this project, but these 2 years to deliver the project was hard work. We did a lot of work to deliver the project, delay mainly due to CSR issues, but after these 2 years of hard work, we delivered the project and we started the project in December 8, 2017. And like that, we stopped the trucking of crude oil and crossing the downtown of Sfax with the road tankers. So this project is a challenging project which aims not only to improve the operating condition at TPS, reduce risk and optimize cost, which is normally done by this project, but also it aims to develop national competencies, Tunisian competencies in terms of engineering, construction and project management of similar projects, which give to Tunisia more opportunities to make such projects in the future. The opportunities offered by this project are mainly reduce road transportation incident, almost zero. Flexible, this project also represents a flexible solution for eventual crude oil quantities increase. So if there is any increase due to future drilling or something like that, we have not a problem to transport our production to CFTP and then to Latrap's terminal. It provides a smooth operation from process to transportation, and like that, by this project, TPS and its shareholders, ETAP and OMV, owns the transportation facilities and have some infrastructure. We move now quickly, very quickly, to some photos. Here, yes, it's a conclusion. The conclusion is this project is very challenging in terms of realization, in terms of opportunities given to Tunisian competencies to apply their knowledge to perform such a project. Here is a very speaking picture. This is the situation before the pipeline. We have plenty of road tankers loading crude oil, so you can imagine the risk. You can imagine the availability, which is very low. You can imagine also the OPEX, it's very high. And here is the pipeline, which is in service and used to transport the crude oil from our CPFs, Biba and tank battery, to CFTP. Some pictures quickly, very quickly. It's a pumping station at Biba. This is pumping station at tank battery. This is the pumping station at CFTP. The metering skid at tank battery. It contains 2 metering bays over gear technology product. Here the chemical injection skid at tank battery. Some photos, there is plenty of photos. Here pig receiver at tank battery. You can see the pipeline, the arrival of the pipeline. And here the pig receiver, the SDV, all this stuff. Pig launcher at tank battery going to CFTP. Metering skid. And thank you for your attention. Thank you very much. Any questions?
Thank you very much for the presentation. Well done for the project. My name is Shokri Shibouk, subsurface team lead for MISCA. My question is very challenging. If you have to do this job again, or this project again, what would you do differently? If you have to repeat this project again, what would you do differently? What are the learnings? What would you do differently?
Thank you very much for this good question. It's a very good question. If I have the opportunity to repeat this project, I will select very well the contractors. Yeah. This is the main important point. I will do more effort to select good contractors. Maybe don't take the lowest price, but take the best contractor. Thank you. Thank you. Thank you very much.
Question for you. I'm Malek Tabet from Fibus Optics. You mentioned in one of your slides pipeline is a project to put a surveillance solution to prevent from intrusion that can happen in your pipelines by these people and by the earth.
Yep, yes. First of all, the pipeline is buried. It's underground. So it is at about 2 meters depth. So it is protected naturally from any sabotism or vandalism or anything. For the protection of the pipeline itself, we are injecting chemical products against corrosion to protect it, to make it run for a longer ride. And we are also cleaning this pipeline, mainly to protect it against corrosion. But for the people, the pipeline itself is buried, and there is some indication to people to don't make any work near this area where the pipeline is laid down. I think this is internationally done like this everywhere in the world.
If someone is coming with a machine and trying to dig without seeing the panel of that you show,
there is indications. It's written before digging, go and call this number or go to TPS and ask for authorization. Yeah, and everywhere in the world is done like this, I think. Also, we have a marshalling. 1 time per week, we are doing the marshalling of this pipeline, controlling this pipeline, to ensure that there is nobody coming with a backhoe or something digging on the pipeline. Thank you. Thank you.
So the next paper. We talk about the application of all system if to boost production of mature liquid loaded high temperature gas fuel at Shell Tunisia Visca. So this presentation will be done. Yes, okay. 1 minute. Okay. Yes is a lead reservoir engineer which has over 9 years of international experience working in various assets within UG Group and Shell. He holds a bachelor's degree in computer science and mathematics from Northwestern University, Boston, and a master's degree in petroleum and geosystems engineering from the University of Texas in Austin. So, yes, no, it's yours.
Hi everyone. My name is Elias Yaish and I'm a reservoir engineer with Shell Tunisia Upstream. Thank you very much for coming to my presentation. I know it's already late, it's 5 p.m. and I hope I'll make it worth your time. But bear in mind, I'm not the last one, so there's still someone else after me. So this presentation is about the application of foam-assisted lift to boost production of mature liquid-loaded high-temperature gas wells. And this project would not have been successful if it wasn't the collaboration between Shell Tunisia and NALCO, but also within Shell, between Shell Tunisia and the center, and also between the different disciplines, between production technology, process engineering, production chemistry, well engineering. So it's really the impact of the collaboration between all these people coming from different backgrounds and different companies that made this successful. And we have with us here from NALCO, Dr. Elias and Karim Zribi, who are sitting here if you have some additional questions for them. So, through this presentation, I will take you through the trial objectives and key considerations. I will touch a little bit on the formal theory, talk about lab testing and chemical selection. I will talk about the facilities risks and mitigation. I will go over more details about the batch trial results, and then I will give you, in conclusion, the key lesson learned and the takeaways. So, you know, the objective of the trial as we always have in Shell, is that we always would like to conduct our operations, our interventions, with zero incidents in terms of HSE, health, safety, and environment. So this is always our first objective, is to do our operations, always keeping you know, good health and safety and environment, so that we don't injure people, we don't impact the environment, and also we maintain the safety of everyone working in the operation. And the second objective was to determine the impact of foam. So it was not really to get production, but to understand the impact of the former on the production, so that we implement permanent facilities that will basically result in improved production or well uptime. So some of the key considerations when we looked at this project were, some of our wells have been liquid loading for some time, and because they have been looking for liquid loading for some time, that water accumulating in the wells have inundated the reservoirs. So basically, you know, when we do our batch, we load some of the water, but we'll have more water coming from the reservoirs, and therefore we may not see really from the beginning immediate results. So we need to do multiple batches to be able to see results, and maybe even if we do multiple batches, that will not be enough. Also, the other consideration is that in our wells, the condensate to water ratio is quite high. So, you know, condensate is a natural deformer, so it's the condensate will prevent the formation of foam when mixing the foamer with the water. So we had really to find a former that can basically be effective in the presence of a lot of condensate. We also dealing with high temperature wells. So when we started looking for a former agent, you know, one of the key things that we realized that was our wells are very high temperatures, and most forming agents, they don't work at such high temperatures. We looked at different service companies, but actually NARCO was the only one to be able to provide with a former that was effective at these high temperatures. And also in the past, some 10 years ago, we tried to inject soaps, soap sticks to try to unload the wells, but that was not successful. So there was already in the company a general kind of attitude that, you know, this trial is likely not to be successful because we have tried this in the past and it was not successful. But, you know, we're trying something different this time. The general procedure was to basically shut the well, pump some former agents from the surface, from the tree cap, and then leave the well shut in for about 18 to 24 hours to allow the former agent to arrive at the bottom of the well, because, you know, these wells are quite deep. They are up to 3,000 meters deep, and therefore it takes some time for the former to arrive at the bottom. Change the former with some water to prevent the former from, you know, because of the temperature, dehydrating and deteriorating. And also agitate the well for about 10 minutes and then leave it for about 6 hours for the foam to appear. So just to touch a little bit on theory, so initially when you produce your wells during the initial life of the field, your wells, you know, your gas wells produced naturally, and the velocity of the gas, which is your gas rate divided by your cross-section area, are sufficient for the gas to lift the water. But, you know, with time, as your reservoir pressure depletes and the performance of your wells deteriorates, the velocity of the gas is not sufficient to lift the liquid or the water. And therefore, you know, you need to look for artificial lift method. And here, you know, we tried foam ejection because in our case it was the most cost-effective method. So to talk a bit on the former, so what does the former do? So the former will reduce the anti-pressure tension between your gas and your liquid phase, creating of some foam, like with soap, liquid soap. It's basically a fancy soap that you use in our well. So it's the same concept. And the foam has lower density, so the mixture of the gas and the liquid has lower density. And because of that, it's easier for the gas to carry the foam to the surface, and therefore carry the mixture of the water, liquid, and the gas. The foam density will be closer to the gas and therefore will be lighter. But the former can cause issues with the separation during the in your facility. So because it basically facilitates the mixture of the gas and the liquid afterward when you want to separate them, it may create some difficulties. So this is kind of the steps we took in our project. So initially, we started looking at the wells, trying to identify which wells were liquid loading, and started looking at whether we can improve the performing by reducing the impact of liquid loading. We took some gas, water, and condensate samples, and we sent them for lab analysis. And then NARCO, did some analysis on the trying different forming agents with our condensate and gas to see which forming agent would be the most effective. And also they looked at different reformers. So in case we have a lot of foam at the surface, what kind of chemical we can use to separate the phases again. We also had to look at doing compatibility testing because you don't know how your chemicals, the former chemicals, will interact with the existing chemicals that you inject in your facilities. And also you don't know how it's going to interact with your production fluids. You have to check that the former, when it breaks down, it does not corrode your tubing, it does not accelerate the corrosion of your facilities. So all this, is very important, and it's really important to do because if you don't properly select your former, you may not get any results, but worse, you may damage or hinder your production. Then, we worked on the design of the batch injection. We decided that we needed at least 4 batches per well to be able to see some results. We also designed how we're going to pump the batches. How much you need to wait for. You need to calculate how much you need to wait for the former to arrive at the bottom, based on average speeds of liquids. We also, put in place the system to how we're going to monitor the well production to determine what impact the former was having on the production of the wells, but also on the facilities and the quality of the separation between the different phases. So, in addition to that, we needed to look at the risks of the facilities of pumping the formers. And some of the risks that we talked about was the chemical compatibility between your former and your other chemicals. So, which can impact, how your existing chemicals are effective in your facilities. So to do that, we did the lab testing. The other risk was, well, if we generate a lot of foam, how can we determine, whether that foam was impacting the separation of the different products in your separator? And to do that, we developed live monitoring of the pressure drop between inside your separator and your gas outlet line. So if we see an increase in the pressure drop, it means that we're carrying some foam inside your gas phase to your gas line. And we also monitored the liquids at the inlet of the separator and at the outlet of the separator. At the inlet to see whether we're getting some foam, and the outlet to see whether we're impacting the quality of the separation. So So this is kind of an overview of the well one performance. So I will be presenting two wells that we did the trial on. So the first well, as you can see here, so the first well, you can see from the upper left, this is the gas rate versus time, and this is the flowing turbine pressure. This is the condensate gas ratio in blue, and the condensate gas ratio in green, and the water gas ratio in blue. So you can see that, this well starting by the end of 2016, severely liquid loading. So the well died actually, and we had to shut in the well for some time for the pressure to build up, and then open the well to flow. And then we started doing what we call intermittent flow. So basically, we let the well flow, and then when it starts dying, we shut it in to enable the pressure to build up. And by doing that, the liquid to be pushed inside the reservoir. And then after about 3 to 5 days, we open the well again, and the well starts producing at about 1 to 2 million scf per day. And because of that, we had to shut the well every time, and this was impacting the uptime of the well. In addition, we're not really producing back the liquid, we're pushing them back inside the reservoir. So we're accumulating water inside the reservoir, which was basically impacting the performance of the well. This is kind of this is a plot of the tubing head pressure versus gas rate over time, and you can see this was when we start doing the intermediate flow injection. Intermediate flow, sorry. So when we shut in the well, so you can see that we have to shut in the well for some time, and then we flow the well, and then we shut in some time, and then you can see the the well slugging and the gas rate. So when we did the batch, these are the results. So on this table you find the average 24-hour gas rate. On this table you find the on this column you find the water gas ratio, and on this column water gas ratio, and this column you find the condensate gas ratio. And you can see that when we did the batches, we did not see really a significant increase in the gas production. But what we saw was a significant increase in your water gas ratio and your condensate gas ratio. So why, from a gas performance, we were not seeing really big upside. We were actually effectively loading the well. So this is important to note, because people will say that, well, this trial was not successful because we didn't see the incremental gas, but we actually were loading the well, and basically the former was being effective in terms of loading the well. And one can basically, by determining this, predict that actually with time the performance of the well would improve. So this is kind of the 4 batches that you injected. You have your gas rate, your water rate, and your shutting turbine pressure. You can see that still the well is struggling to flow gas, but here we started producing much more water. And then following the batch trials, we flowed the well, and actually we found that the uptime of the well had improved by 80%. So we did not require to shut in the well as often to be able to produce it. So this showed that basically the trial was successful, and we were able to increase the uptime of the well from 55% to 80%. This is the second well. So the second well was not did not have as much liquid loading as well 1, but it still had liquid loading. And you can see here your gas rate, your water production in blue, and then your bottom hole pressure. So as the well produces, it started at 3 million, and then start declining as your liquid column start building up. And then at a certain point, the liquid column builds so much that it will be produced to the surface. When it's produced to the surface, you get the big water slug. And basically, by loading that liquid column, your gas rate production get back to 3 million scf per day. So in this case, this well, again, we see from the production of the well that we have severe liquid loading, and we wanted to see whether foam injection could improve that. So this was the result from the well batch injection. So in red here you have the baseline, which is before we did the foam injection, and blue and green you see the impact of the batch number 1 and the batch number 2. So we could see that we increased the production by 1 million scf per day by decreasing the liquid column. And therefore, on average, we have improved the production of the well by 0.4 million scf per day because we need to factor in that the fact that now we need to shut in the well to do the foam injection. Here you can see the plot of the bottom of pressure versus time. So we can see that we decrease the operating bottom of pressure, and therefore we decrease the impact of the liquid column. These are some pictures. So this is the water without the impact of former, and this is the water with the impact of the former. So it's basically milky color because you have a lot of gas bubbles inside it. So as a conclusion, the key for the success of the project was the integration between the different companies, the service and operating company, and also between the different disciplines. The proper planning and design. So really spending a lot of time doing the front-end design, so that you think about all the possibilities and how you can mitigate against the risks of not achieving your goals. The data acquisition and lab testing that we did, and also the fact that you have to have a way of really measuring the impact of the former on your well, so that you're not just looking at the gas rate, but looking at different other parameters to understand how your well is reacting to your former injection. Proper former selection as part of the lab testing, and one of the key lessons learned to take away, I think, from this presentation is that the impact of former is not immediate. So when you do your former injection, you have to think that you're not gonna just inject and see the results. You have to do multiple batches and take some time to see the impact of the former on your production. And it's not necessarily going to improve your gas rate, but it could improve also your uptime, which adds a lot of value as well. It takes some time for the former to reach the bottom of the well, so you need to wait when you inject the former. You need to properly estimate how much time you need to wait. Otherwise, you'll be producing the well before your former has reached the bottom and mixed, and you won't see the result, not because the former is effective, but because the former did not reach the bottom of the well. And also, the most important thing is understand what the well is telling you. It's not just from a gas rate, but you have to understand, your water gas use, your CGR. If you have bottom hole pressure, look at the bottom hole pressure and see how the former is impacting you. Thank you very much. Go ahead.
Thank you for the presentation. So my name is Boubacar Hamadi from Schlumberger. I have two questions for you. The first one is, I don't know if you have tried to create any phase envelope, like to see how much liquid leveling you have in the well. Like before you go for foam injection, did you do any studies related to the evaluation of the well, the calibration of the well, and see the PVT, the phase envelope, and the line of the liquid loading, etc. That's the first one. The second question is, before going for foam injection, did you try to do some analysis related to, let's say, for example, if the bottom hot foam pressure is increasing, did you try to do some analysis on reducing the tubing size, for example, or maybe increasing the wellhead pressure and so on? Thank you.
So, question. So, how did we know that we had liquid loading? So, basically, the analysis was done was to understand, the critical velocity of our wells. And we know that these wells are producing below the critical velocity, and therefore the liquid loading. We also did run, gauge, and and to detect the liquid level in one of the wells. So we ran a downhole gauge and we took a gradient survey, and based on the gradient survey to detect the liquid level, and also also NALCO did some modeling to try to determine the impact of the velocities and on the liquid loading of the wells. So, so the PVT, regarding to the PVT to the phase envelope, I'm not sure we really looked at that, and I'm not sure that's something that really applies in what we've done, because we're not really changing the PVT of the fluids. We're just reducing the interfacial tension between the gas phase and the water phase and the condensate, so that this fluid mix better.
Hello.
So we are far behind this schedule. Thank you again. Yeah. Thank you. Thank you for your understanding. Okay. Thank you. Thank you.
لحظة
Okay.
Magnetic reservoir mapping, white drilling technology, which improves field development results in Southeast Algeria. So this presentation will be done by Mr. Abdelhak Khliver. Abdelhak is a bachelor, is a borehole geologist and well placement engineer, graduated from Governor's University, Faculty of Hydrocarbon and Chemistry in 2010 as a petroleum geologist. Abdelhak contributed during his 8 years in the oil field with Schlumberger in North Africa in processing and geological interpretation of fault line and logging while drilling images, fractures, and structural analysis for geological modeling, also leading steering horizontal wells project in 10 countries for different operators.
For presenting me. I would like to thank the audience to bear with us late this time, and thank you for attending my presentation. I'll be talking about the reservoir mapping while drilling technology using the ultra-deep electromagnetic directional measurement to drill horizontal wells and that contribute in field development projects. You might ask what this link to the production and project development, and I will ensure you that everything will fall at the end into the production. In any project, field development project, we have a plan which composed on 3 phases after the seismic and prospection. The first one consists on the exploration phase, where we drill a couple or few wells, exploration wells. After which, the second phase, which is the appraisal wells, where we try to delineate our field and reserve for reserve estimation. And then the second and the third phase, which is the development phase, where we drill more wells and essentially the horizontal wells that will contribute more on the production. Taking the example that of southeast of Algeria, one of the operators, where they start their plan in 2003, they start their first exploration wells, and till 2009, it was mixed between exploration and appraisal wells. And then in 2009, they start their first horizontal well as a try to see the contribution of the horizontal wells into the production and how effective that's compared to the vertical wells. They had a break in 2013 to evaluate what they had, if they had to change their strategy or not to keep the vertical wells. And from 2016-17 to 2018, they put a plan to drill up to 30 wells, in between up to 10 horizontal wells. So the strategy from 2016 up to now is to drill more horizontal wells that essentially contribute into the production and increase the production for this field. Historically, and to drill a horizontal well, it might seem to be easy. We just need to put a plan where we need to define 3 targets: the entry point of the reservoir, the landing point inside the reservoir, and the TD point, which determine the length of the horizontal section. This seems to be easy, but the reality is always different depending on the geology that we are drilling in. And in some cases where we have to cross faults that lift up the reservoir up or take down the reservoir down, so we have to find a solution to interactively adjust our trajectory in real time to be always inside the reservoir. And this is called the well placement, or in the industry as the geosteering. If we want to define it, it's the planned interactive placement of the wellbore using geological criteria and real-time measurements. All this goes in one goal, is to maximize the return of investment, because we are putting money and we need return. And the return comes by footage per day, how many meters of foots we drill per day, by reducing the drilling flat time and increasing the ROP, which is the drilling speed. And in second hand, which is talking about the reservoir exposure, by enhancing the reservoir description by maximizing the reservoir contact. Historically, the operators in oil field, if they want to drill horizontal wells, what they do as first step is to drill a vertical well, which is called a pilot well. They define the structure, the top of reservoir, the oil-water contact if existing, after which they sidetrack the vertical well and go to the drain section, the horizontal section. So at the end, we end up with 2 wells with only 1 producer. So what we propose to them is to eliminate the need to drill this pilot well and go straight to the horizontal section, reducing the cost of drilling this pilot well, which sometimes goes up to $1 million or even more, depending on the services that they run into this well. So we go directly to the lateral section using the technology that we provide, the reservoir mapping while drilling technology. You might ask me what this consists, so how we can eliminate the pilot well. Sorry. So imagine we have this overburden, the shale, and then the reservoir, sand, and if you can, if the water plan, if we can say it. So this is our well. This is the bit. So before we enter the reservoir, we can see with this deep electromagnetic signal up to 30 meters, we can confirm the top position, the depth position, and this allows us to adjust our trajectory and for better landing depth. After landing, we will be able to see even the fluid contact, which is the water contact, if it's within the range of detection up to 30 meters. And by this, we adjust our trajectory in real time while drilling to land the well in the target zone of the reservoir. So our solution, to apply our solution, we need to redesign the BHA, the drilling BHA, to drill this and acquire the needed data for us to take the decision. So in one hand, we need the drilling technology, the rotary steerable technology, RSS, that can control the direction of the trajectory in 3 dimensions, and also can enable us to control the trajectory and minimize the vertical section or the kickoff point parameters for the trajectory. And in the second hand, we need the logging while drilling tools and technology that enable us to map and acquire the petrophysical data and geological data to take the decisions in real time. So the proposed technology is called the geosphere. It's like one transmitter sub and 2 receivers separated, and we can change the configuration based on what we want to achieve and which depth of investigation we want to map. So we have this here, the transmitter, and then the first receiver will give us a short spacing up to 15 meters depth of investigation. The second receiver, we call it the long spacing depth of investigation, so up to 30 meters of mapping. This tool is a resistivity seeking tool, so it maps any resistivity contrast. So the higher the contrast, the further we can see inside the formation. And as you know, we have 3 parameters that control how far we can see. We have the frequencies that we are firing this electromagnetic signal with. The lower the frequencies, the further the signal will travel into the formation. And the spacing between the transmitter and receiver. So that's why we are configuring interactively our BHA to achieve, to capture the maximum of signal for us. And then there's a third parameters, which is the formation resistivity, which we cannot control. So the response of this technology depends from a reservoir to another one based on the formation resistivity. To show you in reality how this technology apply and the results of this technology, I'm showing you an example here from North Sea, just to illustrate this. So they have seismic and some horizons, and this is the reservoir zone, which is a sand injectite environment. As you know, the seismic have limitation and uncertainties because of the velocity conversion. So it cannot resolve below 20 to 15 meters. So we have a huge uncertainty in terms of depth of the reservoir and position. And also uncertainty about the thickness of reservoir and horizontal parallelism, let's say. So if we zoom in into the reservoir, because it's sand injectite, it doesn't have a horizontal shape of layers, but the sand can go anywhere depending on the stress applied of the overburden. And it's difficult to map. If you drill, for example, a well here, this is the response where we got from the gamma ray that tell us that is a clean sand, and the typical response of the sand filled with hydrocarbon, which is higher resistivity. If we put another well here, because of the, as I said, lateral variation of the sand injectite and this environment, so we have different response. and we cannot map the whole reservoir with the same philosophy. So if we put the distance to boundary technology to geosteer the well into the target, we will see some variation change at local scale, at 5 meters up and 5 meters down from the well bore, but it doesn't resolve for the large scale of the reservoir. So by using geosphere reservoir mapping wire technology, it gives us a full picture of the reservoir. So all what you can see here in blue is non-reservoir, considered as shale, and everything which is reddish, considered as sandstone reservoir, that in this case is filled by hydrocarbon, so it's producer. We can, even by having this, what we call it inversion, we can map the top and base of the reservoir and export it to update our static modeling that will be used into the dynamic model for the reservoir engineers, for example, to do the work. This is the example of North Sea. Now we'll move to the example of Algeria. So for confidentiality reason, I will not show a lot of details, but I'll just try to give you the idea of what we did and what we proceed into this. So this operator is operating in southeast of Algeria. So they had the main target reservoir, which is the fluvial system. Yeah, a braided channel complex system. So this is how it looks like in the old geological age. In this time, so it's a 4 stacked channel system, all superposed into the one above the other. So it's consists a reservoir of up to 30 meters of thickness, 29 to 30 meters, that represent the best reservoir in this area, which is the Triassic reservoir. As I said in the beginning, they were to drill the horizontal wells. They were planning for a vertical well, pilot well, and then go for the horizontal well. So we proposed to them to use this technology in the first well in 2016 to go straight to the lateral section, landing section, and the results were impressive. So as you can see here, we start seeing some layers above the reservoir, and then we map the reservoir up to 15 meters above before we hit it. We adjust our landing point below the gas oil contact, and at landing point we confirm the position of oil water contact, because they had the general field oil water contact, but it has some uncertainties. So we confirm the position of the oil water contact, and this helped them to better estimate their reserves and the effective thickness of their reservoir. Of course, the next section will be drilled up to 600 meters, if I remember, horizontally, using distance to boundary technology for proactive change into the lateral section. After evaluating the results of this well, they were happy and impressive of this technology that saved them, as I said, up to $1 million per well. So they were excited to use it in the other wells. So in 2017, we drilled with them 2 other wells with the same technology. We could, yeah, thanks. We could map the reservoir, top of reservoir, and also the oil water contact to place the well at the top of the target zone. The third well, which was a bit challenging compared to the 2 first wells, because the formation came up around 10 meters above the expected top, and we had to react to proactively change our trajectory and landing point to be inside the reservoir. And fortunately, operation were helping us a lot to achieve these results. As a conclusion of this project, we successfully placed the 3 horizontal wells. We landed them and drilled them horizontally into the target zone with 100% net to gross. Cost saving of 20% from the original budget of this horizontal well, using eliminating the pilot well. Fully mapping of the reservoir extension, thickness and lateral variation, and also mapping the oil-water contact position. Optimized oil production and recovery, avoiding early water breakthrough by placing the well in the right position and the optimum position to maximize the life of the well. And this technology became the preferred practice for this customer in their field development with drilling the horizontal wells. You noticed me, I was focusing only on the landing part, but this technology have different many applications. I'm sitting here just 3, but we have different applications. If we try to think about the ultra-deep electromagnetic signal, how it moves into the formation, how we can capture it, even the algorithm, how we can we change them to capture even the ellipsoid of the electromagnetic signal. So we use this technology in the landing application to place the well in the right spot without losing a lot of budget. Even geosteering inside the reservoir in the lateral section. In this case, as you can see, this reservoir is pitching out, so we knew more than 100 meters that there is another reservoir above us. So the decision here was easy to build up the inclination and go target this reservoir. And the third application is the reservoir mapping. Once we map the position of the ton and clays, we can export them, update the models, static model for the future wells. If I want to summarize my presentation in one sentence, I can say there is no place left for hydrocarbon to hide. Thank you. Any question? Or
too late today. So sorry. Thank you for your effort. Thank you for valuable presentation. Thank you.